Hey everybody, Dr. A here, and in this video we're going to be exploring an example of using Castigliano's method to compute the displacement of a truss joint. So let's go ahead and dive into it. In the given information, we're being asked to compute the vertical displacement of joint B, and we're being told that the axial rigidity, which is AE, the product of cross-section area and modulus elasticity, is constant for the entire system. So let's look at the system we're given here. Here we have kind of a classic 3-bar truss. We have a member AC, which is vertical and 6 feet long. We have a member BC, which is horizontal and 8 feet long. And then we have our diagonal member AB, which will end up being a 10-foot length once we, think about the Pythagorean theorem there for that geometry. And then we have a single point load of 150 pounds at point B. Now, if you recall, we did an example very much like this. I think it's actually identical to this using virtual work a couple videos back, and we got the solution that particular way using virtual work. Now, with Castigliano's method, we should get the exact same final answer as we did using virtual work. Remember, Castigliano's method is also a type of energy method, okay? So let's go ahead and get started. Under the solution, what we're going to do is we're going to kind of consolidate steps 1 and 2. For Castigliano's method, steps 1 and 2 basically say place a variable force P at the joint of interest in the expected direction of displacement. So in this case, we're going to place the variable force P downwards at joint B. Okay. Now, when we create this particular system here, it's going to be similar to a virtual system, although we're not going to call it that because this is a different method than virtual work, although it is similar. Now, the big difference here is when we place this variable load P at joint B, we are going to keep the real load here, okay? Now, if you think back to virtual work, we took the real loads off of the virtual system when we did a virtual work analysis. For Castigliano's method, we're going to place the variable load P at joint B, but we are going to keep the 150 there, okay? So I'm going to turn the page, and let's go ahead and draw what that system would look like. So I'm going to sketch it over here. Got my horizontal member, got my vertical member here, got that diagonal member here, and we're gonna have the roller at A, the pin at C, and this is 6 feet long, this is 8 feet long. So what's gonna happen at this joint over at B? Well, here we're going to say P plus 150 pounds. So again, we're putting the variable load there, but we're keeping the 150 there. So it's like they're stacked on top of each other, okay? And there's joint B. So what do we do next? Well, in step 2 of the process, we use, method of joints to get the member forces, okay? So here I'm going to say free body diagram of joint B. And so here I've got the P plus 150 pounds, and then I have capital F BC, and of course I have FAB, and we know that we have a 3-4-5 ratio here, okay? And so by method of joints, I can say sum of the forces in the y direction equals 0. And so I'm going to have minus, open parentheses, P plus 150 pounds. And then I'm going to have minus FAB times 3/5 equals 0, okay? And so I'm going to do some rearranging, and I'm going to get FAB equals negative 1.667 P minus 250 pounds, okay? So remember, be careful with your algebra. This negative is going to distribute to both terms. That's where these two negatives come from, okay? So that's FAB, and notice this is FAB as a function of that load P, all right? Next, I'm going to do sum of the forces in the x direction equals 0, and here I'm going to say minus FBC plus FAB, so this is going to be plus 1.6667, put one too many sixes there, 1.667 P plus 250 pounds, okay? And then that collectively is going to be multiplied by 4/5 equals 0, and I can solve for FBC to be 1.333 P plus 200 pounds, okay? Now here's a question for you. How come this 1.667 P plus 250 is positive where I had negatives earlier? Well, remember, when we include these negatives here, what that really means is that FAB is in compression, pointing at joint B. Now, if it's in compression at joint B, which means it's pointing at joint B, that means that it's going to have a positive x component pointing to the right, which is why it's showing up as positive here, okay? So again, remember your method of joints. This is still, at this point, it's just method of joints. The only real difference is you have this variable P kind of floating around in your equations, okay? Now, finally, we're going to move to joint A, and we're going to say free body diagram of joint A, and I'm going to sketch that here. I'm going to have an FAC. I do have an AX here, but remember, you're not really interested in the reactions here. You're just interested in the member forces. And I have this FAB in compression. So, you can write FAB here is 1.667 P plus 250 pounds. And again, I'm writing it as positives here because I'm showing the fact that it's in compression pointing at joint A here. So if I show that this vector is in compression pointing at A, then I should not be writing the negatives there, because the fact that this is pointing at A accounts for the fact that it's in compression, okay? And so here I'm going to say sum of the forces in the y direction equals 0, and I'm going to say negative 1.667 P plus 250 pounds, and that's going to be multiplied by 3/5. Remember, this is at a 3, 4, 5 slope, and then of course we're gonna add on there plus FAC equals 0. So I kind of had to wrap this equation around here. We're going to do some rearranging, and we'll get FAC is simply a positive P plus 150 pounds, okay? Why is this negative here? Again, from method of joints, this is in compression pointing at joint A, which means it has a negative Y component. So that's why the negative shows back up again. And remember, this whole thing, this whole quantity is negative, okay? So now I've got my 3 member forces as a function of P, load P. Now what I'm going to do is I'm going to go to the next step of my my process, and I'm going to find the partial derivatives of each one of these forces with respect to P, okay? So if I turn the page here, I'm going to say partial derivative df of AB with respect to P. And so when I find that partial derivative of the force AB with respect to P, what does that mean? That means I use the other term as a constant, right? And so this just comes out to be negative 1.667, okay? And then similarly, I'm going to have the partial derivative of the force in BC with respect to P, and that's positive 1.333, and then I've got the partial derivative of the force in AC with respect to P, and that's just going to be 1, okay? So that's the next step in my Castigliano process. Now, finally, what I can do is set up a table and help myself piece all of this together. So I'm going to turn the page again, and I'm going to generate a nice organized table. So I'm going to write member here, okay? And then I'm going to write the force as a function of P. And then I'm going to write dF dP, have a column for that. And then I'm going to generate another column. This is going to be the force when P equals 0. If you look back in our Castigliano process, part of our procedure involves us getting the force by setting P equals to 0. So that means we'll just get the regular real forces in each member. And then, of course, I'm going to have a length in feet. And let's make this table a little bit longer. And then finally, I'm going to have a column for F times dF dP times L, okay? So I'm going to have this for member AB, member BC, and member AC. So those forces as a function of P, that's negative 1.667 P minus 150. And I'm sorry, that was minus 250, not 150. What am I thinking? Minus 250, there we go. And then I'm going to have 1.333 P plus 200 for BC, and then I'm going to have P plus 150 for member AC. Those partial derivatives are negative 1.667, positive 1.333, and positive 1. And then F, when P is 0, is 250 pounds, 200 pounds, and 150. How did I get that so fast? Well, I just set P equal to 0 back in this column, and I'm left with these constants. Be very careful here. I almost missed that negative. That's negative 250, right? Negative 250. Those lengths are 10 feet, 8 feet, and 6 feet. And then I'm going to come up with this last column, which has this product. So what are these? What is this product? This is going to be the product of F when P is 0, the partial derivative, and the length L. Okay, so I'm going to multiply these three together, and I'm going to do that for each row. So I'm going to get 4167, and then 2133, and then 900 for that last row, okay? Now, let's talk about the units here. I'm going to kind of sneak the units here in blue. Remember, this first column here, the force, that carries units of pounds, okay? So we definitely have those pounds hanging out there. What about dF dP, okay? What about this? This is going to be unitless, right? You're finding a rate of change of a force with respect to another force. So these coefficients here are going to be unitless, all right? Which makes sense because it's really P back here that carries the units of pounds along with these constants out here, okay? So this is a rate of change or unitless. Okay, what about these F forces here in this column? Again, these are going to have units of pounds. And then we already have the length in feet here. That was pretty obvious. And then what about the units of this last column over here? Well, you're going to have pounds times unitless times length in feet. So this is going to carry units of pounds. Let me write that a little bit better for us. Pounds times feet here in this column, okay? And so what do I do next? Well, I apply Castigliano's theorem. Castigliano's theorem says that the displacement, the vertical displacement of joint B, so that's delta VB, V is for vertical, is equal to what? Well, I've got that formulation, summation as I goes from 1 to 3 of what? Of FL over AE sub I times DF sub I dP, okay? And so let me ask you a question. How do we come up with this expression from this table over here? Well, look at what we have here. This F dF dP L, where is that? Well, that's this FL dF dP. And so for our problem, 1 over AE was constant for all members. In fact, the problem statement told us that. So guess what we can do here? We can say 1 over AE times the sum as I goes from 1 to 3 of this FL times dF dP, okay? And what we have here in this bracket is this column right here, just algebraically slightly rearranged. So what we do is we add these three numbers together, okay? So I can put a little sum here. If I add these three together, I should get right about 7,200 pound-feet, okay? And so going back to our final version of the solution, this is going to be 7,200 pound-feet over AE. And it came out positive, which means this is displacing downwards, which is the direction that we placed P. Okay, so we'll make a little note here. Note delta VB is downwards, which is the direction of load P that we put on the system earlier, okay? So this is our final answer, and would the units make sense? Do the units check out? Yeah, they should. You know, A is gonna have units of length squared. E is going to have units of force per length squared. So you get the length squared terms canceling between A and E, and then you're left with just a force term in this denominator, which will cancel with a force term in the numerator. And then finally, you will just have units of length, which is what you should have since this is a displacement. In some of my other videos, I show some work on managing those units. I would encourage you to maybe pause the video and show that unit check for yourself on your own this time, okay? And again, I've done unit checks like this in my other videos before, so you give it a shot on your own this time and make sure you pop out units of just length for delta. So that wraps up this video. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.